In this lesson, we're going to take everything you've learned about binary and hexadecimal and apply it to something that you'll encounter constantly in cybersecurity: IP addressing and subnet masks. If you weren't sure why we spent so much time practicing binary conversions and learning hexadecimal, this lesson helps bring it more together. IP addresses are quite literally binary numbers. Understanding how to read them in binary is essential for network security, firewall configuration, intrusion detection, and countless other cybersecurity tasks. The goal for the end of this lesson is that you'll feel more comfortable looking at an IP address and understanding what's happening at the binary level. I want to help you understand how subnet masks work to divide networks, and you'll see why hexadecimal shows up in IPv6 addresses. These skills will serve you throughout your cybersecurity career. So we're going to start with IPv4 addresses, which you've probably seen hundreds of times. A typical IPv4 address looks like 192.168.1.100, but a lot of people don't realize that that is not really how computers see that address. That dotted decimal format is just a human-friendly version. To a computer, an IP address is a 32-bit binary number. An IPv4 address consists of 4 sections separated by dots. We call each section an octet because each one represents 8 bits of data. 4 octets times 8 bits equals 32 bits total. When you were practicing those 8-bit binary conversions, here is one of the places where that skill becomes essential. Let's convert 192.168.1.100 to binary, 1 octet at a time. So if you want to pause the video and try to do this yourself first, that's a good idea because you have the tools already. And if it's a little bit hard for you, that's a good thing. Starting with 192, using our 8-bit place values of 128, 64, 32, 16, 8, 4, 2, and 1, we need to figure out which combination adds up to 192. So we ask, does 128 fit into 192? We're going to go from left to right in this case. The answer is yes. There are 64 remaining after that. So then does 64 fit into 64? Obviously yes, and there's 0 remaining. So 192 in binary is 11000000. How about for 168? Does 128 fit? You can see that it does, and it leaves 40. Does 64 fit into 40? No, it doesn't. Does 32 fit into 40? Yes, it does, and then you have 8 remaining. So then does 16 fit into 8? No. Does 8 fit? Yes, and that leaves 0. So 168 in binary is 10101000. For 1, this is straightforward. 1 in binary is 7 zeros followed by a 1. Notice we still use all 8 bits, padding with zeros on the left. For 100, does 128 fit? No. 64? Yes. And we have 36. So then does 32 fit? Yes. And we have 4 left over. Does 16 fit? No. Does 18 fit? No. Does 4 fit? It is 4. So yes, and that leaves 0. So 100 in binary is 011. 00100. Then you put it all together, you have 192.168.1.100 in binary is 11 with 6 zeros dot 10 10 10 with 2 zeros dot 7 zeros and a 1 dot 01 100 100. There you have your 32 bits, which gives us over 4 billion possible unique addresses. Now specifically 2 to the power of 32 equals 4,294,967,296 possible combinations. Let's think about a few real-world scenarios where this knowledge becomes important. Understanding network boundaries is one. When you're analyzing network traffic or configuring firewalls, you need to understand which IP addresses belong to the same network and which are on different networks. This determination happens at the binary level. We'll see more of that when we dig into subnet masks. Another reason, we've got firewall rules. Many firewall configurations and access control lists work with IP ranges expressed in ways that only really make sense if you understand binary. When you see a rule that blocks 10.0.0.0/8 Understanding the binary helps you immediately figure out which addresses are affected. Another reason it's important is for analyzing network attacks. If you're investigating a security incident or studying malware behavior, understanding IP addresses at the binary level helps you identify patterns, recognize spoofed addresses, and understand how attackers might be manipulating network traffic. And there are many, many other ways. I'll just mention one more of working with intrusion detection systems. Tools like Snort and Suricata use rules that often reference IP addresses in ways that require binary understanding. Being comfortable with binary makes you more effective at writing and interpreting these rules. So let's think about the binary boundary of subnet masks. A subnet mask is a 32-bit number that determines which portion of an IP address identifies the network and which portion identifies the individual host on the network. You can think of it like a street address. In the address 123 Main Street, Springfield, you have two pieces of information. The street name tells you which road to find. The number tells you which specific house on that road. An IP address works similarly. Part of it identifies the network, and part identifies the specific device on that network. The subnet mask is what tells us where to draw the line. We can look at a common subnet mask of 255.255.255.0. Converting each octet to binary, we know 255 is all ones, and then we know 0 is all zeros. So 255.255.255.0 in binary is 8 ones.8 zeros. You see, all the ones are grouped together on the left, and all the zeros are grouped together on the right. And this is always true for valid subnet masks. The rule is that the ones in the subnet mask identify the network portion of the IP address. The zeros identify the host portion. In this example, the first 24 bits, 3 octets, represent the network, and the last 8 bits, 1 octet, represents the host. So with our IP address of 192.168.1.100 and a subnet mask of 255.255.255.0, we can see we have these IP address and our subnet mask, and the network address is 192.168.1, the first 3 octets, and the host address is 100, the last octet. Any device with an IP address from 192.168.1.1 through 192.168.1.254 would be on the same network. Now we have binary shorthand with the CIDR notation. You'll often see IP addresses written with a slash and a number, like 192.168.1.0/24. This is called CIDR notation, which stands for classless interdomain routing. That number after the slash tells you how many bits are used for the network portion. In /24, the first 24 bits are the network identifier, which corresponds exactly to the subnet mask 255.255.255.0 because 255.255.255.0 has 24 ones followed by 8 zeros. So remember, we had the first 3 all ones. 3 times 8 is 24. Think about some common CIDR values and their subnet masks equivalents. /8 means 8 network bits, leaving 24 host bits. In that case, the subnet mask is 255.0.0.0. In binary, that's the first 8 are ones, and the next 24 are zeros. This is a huge network with over 16 million possible host addresses. /16 means 16 network bits, leaving 16 host bits. The subnet mask is 255.255.0.0, and in binary, we know our first octet's going to be all ones, our second is going to be all ones, and the last 2 are going to be all zeros, so it's split half and half. This provides about 65,000 possible host addresses. /24 means 24 network bits, leaving 8 host bits. The subnet mask, 255.255.0 in binary, the first 3 octets are ones, the fourth one is zeros, giving us 254 usable host addresses. /32 means all 32 bits are the network portion. This represents a single specific IP address with no host range. Understanding CIDR notation is essential for cybersecurity work because you'll see it constantly in firewall rules, access control lists, routing tables, and security documentation. For example, if a firewall rule blocks traffic from 10.0.0.0/8, you now understand that it's blocking any IP address where the first 8 bits match the first 8 bits of 10.0.0.0. Since 10 in binary is 4 zeros followed by 1010, any address starting with 10.0 x.x.x is blocked. That's the entire range from 10.0.0.0 to 10.255.255.255, over 16 million addresses. Now, things get more interesting when the subnet boundary does not fall neatly on an octet boundary. Consider the subnet mask of 255.255.192. If we convert that last octet, 192 in binary is 11, followed by 6 zeros. So the full subnet mask in binary is all ones for the first 3 octets, and then 11, followed by 6 zeros. That's 26 ones, making this a /26 network. The network portion uses 26 bits, leaving only 6 bits for host addresses. With 6 host bits, we can have 2 to the power of 6, which equals 64 total addresses. But we subtract 2 because the first address is the network address, and the last is the broadcast address, giving us 62 usable host addresses. This is called subnetting, and it's how network administrators divide larger networks into smaller, more manageable segments. From a security perspective, subnetting allows you to create network boundaries that can be protected with different security policies. You might put your web servers on one subnet, your database servers on another, your employee workstations on a third subnet. Then you can configure firewalls to control exactly what traffic can flow between these segments. Now, we talked about hexadecimal mattering for IP addresses, and that's IPv6. As we've touched on before, IPv4's 32 bits give us about 4 billion addresses, which seemed like plenty in the early days of the internet, but we've essentially run out of IPv4 addresses at this point. So they came up with the solution of IPv6, which uses 128 bits instead of 32. 128 bits gives us an astronomical number of possible addresses, 2 to the 128th power. That's about 340 undecillion addresses, or roughly 340 trillion. There are enough IPv6 addresses for every grain of sand on Earth to have billions of addresses. But writing out 128 bits in binary would be absurdly long. Writing it in decimal would give us numbers in the decillions. So IPv6 uses hexadecimal notation. An IPv6 address consists of 8 groups of 4 hexadecimal digits, separated by colons. And you've seen these kinds of examples before in the previous lessons, but you can see it again here. Each hexadecimal digit represents 4 bits, 1 nibble, as we learned. So the 2 is 4 bits, the 0 is 4 bits, the 0 is 4 bits, the 1 is 4 bits, the 0 is 4 bits, the D, the B, the 8, each one 4 bits. Each group of 4 hex digits represents 16 bits. So between, before, after the colon, we've got 16 bits. 8 groups times 16 bits equals 128 bits total. So we think about how we said that nibbles were the bridge between binary and hexadecimal. If you see a hex digit like A in an IPv6 address, you immediately know it represents the binary value of 1010. So if we think about that first group of 2001, the 2 in hex is 0010 in binary. The 0 in hex is all zeros in binary. Again, and then the 1 is 0001 in binary. So we know that 2001 in hex is 0010 with 8 zeros, and then 3 zeros and a 1 in binary, which is 16 bits. Let's think about some more specific cybersecurity scenarios where this knowledge is helpful. If you're analyzing log files, when you're reviewing firewall logs or intrusion detection alerts, you'll see the IP addresses constantly. Understanding the binary relationship helps you quickly identify whether addresses are on the same subnet, whether they fall within trusted ranges, and whether the traffic patterns make sense. It's all about the patterns. When you configure a firewall to allow or deny traffic, we're going to specify the source and destination addresses using CIDR notation. A miscalculation here could leave your network exposed or accidentally block legitimate traffic. Now, attackers often manipulate IP addresses or exploit weaknesses in how systems handle network boundaries. Understanding binary helps you spot anomalies and track attack paths. When you're analyzing network packet captures, you'll work directly with binary data. The IP headers contain source and destination addresses in their raw binary form. Understanding NAT and private addressing, the private IP ranges such as 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16 are defined by their binary boundaries. Knowing these ranges and how they're structured helps you understand network architecture and identify potential security issues. So for just a quick summary, IPv4 addresses are 32-bit binary numbers displayed in dotted decimal format for human readability. Each of the 4 octets represents 8 bits and can have values from 0 to 255. Subnet masks use binary ones and zeros to define the boundary between the network portion and the host portion of an IP address. The ones always come first, followed by the zeros. And CIDR notation provides a shorthand way to express the subnet masks by indicating how many bits are used for the network portion. A /24 network has 24 network bits and 8 host bits. So whatever is after that slash, you just subtract that from 32 to know how many host bits there are. An IPv6 addresses use that hexadecimal notation to represent 128 bits in readable format. Each hex digit represents 4 bits, and your knowledge of nibbles makes converting between hex and binary straightforward. So these are skills that form the foundation of network security work. Every time you analyze traffic or configure a firewall, investigate an incident, or design a secure network architecture, you're going to have to draw on your understanding of how IP addressing works at the binary level. So now it's a good idea for you to practice converting IP addresses and subnet masks between decimal, binary, and CIDR notation. The more automatic these conversions become, the more effective you're going to be as a cybersecurity professional.